everyone, Mrs. Woodruff here. Today we're going to take our ideas of exponents a little further and start talking about graphing exponential functions. As we go through this today, I'm hoping you're going to have a bit of a deja vu feeling because we have talked about graphing exponential functions in our Unit 3 function families discussion. We've also seen this curve a lot in the news lately as we've talked about flattening the curve. You'll notice that an exponential curve can have this sweeping up where it kind of starts gradual and then it kind of takes off. So that's kind of what we expect when we see an exponential function. Before we get there though, why don't we take a minute just to revisit our function families and see what you remember from our Unit 3. What I've done here is create a slide that has equations over at the left, and then behind each of these boxes would be the name of the family. And then over here, just sort of a brief description of what the graph looks like. What I'd like you to do right now is to pause the video, take out a piece of paper, and see how much of this you remember. We'll come back in a minute and see how you did. Hi guys, here we are. Let's see how you did. So function family, y equals mx plus b. This is our linear. We did a whole 2 units on this, linear functions, and then we did systems of linear functions. Of course, the graph would be a line. Here we've got a variable exponent. We've got a number times a base raised to a variable. That should be our exponential. And we're going to expect that curve that either has a rapid growth or a rapid, what's called decay. The next one, notice the input variable is being squared. That is going to be our quadratic. And we are expecting to see the u, which we call a parabola. It's kind of u-ish. The next one has the absolute value. And whenever we see absolute value, we are expecting the v. Next up, I see a square root there, and that will be the square root function. It's the parabola, the u, actually laying on its side, and we only have half of it for it to be a function. The next one is the cubed. So it is the cubic function, and this is the one that has a curve, and I call it the hurricane symbol, and it goes in the y direction. Now the next one is the cubed root, and that still has that same hurricane symbol, but it stretches out in the x direction. This was the greatest integer function, or also known as the step function, and it looks like a series of steps or a staircase. And this one is the ones that you guys weren't crazy about. This is the piecewise function. So a piece of one, a piece of another kind of function. And, you know, it depends on what functions you're graphing here in order to be able to describe the graph. So what we've covered so far really in terms of our mastery of function families is we did linear functions in Unit 4 and then systems in Unit 6, and those are both completed. We're working on exponential right now, and we're actually a little bit more than halfway done. And then we'll finish off the year doing the quadratics. So let's go back and just remember kind of what we talked about with an exponential function. And this kind of idea was actually in our very first unit where we talked about geometric sequences. And we, in that unit, talked about exponential growth and decay. This is our basic exponential function right here. You'll see that A is our initial population or the initial amount of money or whatever we started with. The B is either a growth or a decay factor. And you're going to remember that it was growth if it was greater than 1 and decay if it was less than 1. And if the B equaled 1, the function didn't change. And the exponent of x is the number of time periods, or the number of generations. And our y, our output variable, will be the population or the amount of money after x generations. So here are 2 examples down the bottom of exponential functions. You'll see one here has a base of b, a factor that is greater than 1. This would be a growth. We'd expect it to go up. In this one, notice the b, the factor is less than 1. We would expect it to go down. So this is a growth, and this would be a decay. So let's just look at a real world situation here, where we start off with 20 rabbits on an island, and then that rabbit population triples every year. How many rabbits would there be after 4 years? So our initial amount of rabbits is 20. After 1 year, if we tripled that, 20 times 3 would be 60 rabbits. So basically what we did was we took that initial amount and we multiplied it by 3. Now that new population of rabbits the next year would triple again. So the 60 times 3 would be 180. So if you took that initial population times 3 and then tripled it again, we would get 180. Now that 180 is going to be multiplied by 3. So after 3 years, there'd be 540. And if we kind of write it out as an expression here, you'll see there's the 20 times 3 times 3. There was after 2 years, and now after 3. And then if we go to 4 years, we'd be up to 1,620. And we would have multiplied that initial population by 4 factors of 3. And there would end up being 1,620 rabbits. If you look at this right here, you can see the formula developing with there's the start amount, and then it's times a base of 3, that factor of 3, and the x would be replaced by how many years. So if we put a 1 in for x, we would get the 60, and if we put the 2 in, we'd get the 180, and you can kind of see where this formula develops. When we plot those points, so these are the points we just got. Let me just go back. Remember that there was 1 year 60, 2 years 180, 3, 540. And if I plot those points here, you can see the growth coming of the rabbit population. So just to go back, let's evaluate an exponential function for the domain. We're going to put these x values in for x. We're going to substitute. And now our exponent rules are going to come into play that we've reviewed recently. So we would first of all have an x of -1. So 5 to the -1. Remember, a negative exponent is going to drop that to the denominator. It's going to put it in the other place, and it would be 1 over 5 to the +1, which is a decimal of 0.2. The next one, if we put in 0, 5 to the 0, anything to the 0 power is 1. And then if we put in input 5 with an exponent of 1, 5 to the first would be 5. And then it kind of gets easier from here. 5 squared would be 25. 5 to the third would be 125. And here's where you're going to see it start taking off. 5 to the fourth would be 625. And if I wanted to graph this exponential, I now have coordinates where -1, comma 0.2, 0, comma 1, 1, comma 5, 2, comma 25, and so forth. And I could graph that exponential. Okay, so here's another one. We're going to graph this function. So notice I've got the fav 5 coming back over here. So I'm going to replace the x and substitute in a -2, a -1, a 0, a 1, and a 2. When I take the -2, remember that this negative exponent is going to drop that down to 1 over 2 to the +2, which is 1/4. We end up with 3/4 here, or 0.75. So there's our coordinate pair. The input's -2, the output's 0.75. The next one, if I put in -1, that's going to bring this down to the denominator as a +1/2. I end up with 3/2, or 1.5. 2 to the 0, of course, anything to the 0 is 1. Multiply it by 3. My output is 3, and I've got 0, comma 3. 3 times 2 to the first, I'm going to get 6. So 1, comma 6. And 2 to the second, 2 squared is 4, times 3 is 12. And I now have 5 points that I can plot. We will use regular graph paper for exponential functions because they grow too fast to be on the coordinate graph paper, and we often are only using quadrants 1 and 2, so we use just regular graph paper. So here you're going to see me graphing. Here's the points we just got. This one I did graph on, weirdly enough, on the coordinate graph paper, but you're going to see I'm already off the graph paper up here. Now there's just some things I want you to notice. I want you to notice that the y-intercept is 3, so where x equals 0, y equals 3, and notice the 3 right there, that's our start amount. Notice that the y is never negative, it's never coming down below the x axis. The graph approaches the x-axis here, and it gets closer and closer and closer, but it actually never reaches it, because if you think about it, as you put like a -1 in here, you've got 1 over 2. When you put a -2 in here, you have 1 over 4. When you put a -3 in here, you have 1 over 8, and then 1 over 16, 1 over 32. It's getting closer and closer to the number 0, but it will never reach it. The x-axis acts as something called an asymptote that you learn about later in math, but I thought I'd just give you the word today. So it'll never touch the x-axis. So just to check, what I would do right now is kind of get your calculator out and just make sure that you're inputting things into the calculator correctly. If I was in the classroom, I'd kind of be doing a check. So what I want you to do is, if your function is f of x equals 0.2 times 10 to the x, I want you to input a -2 into the calculator. Just check, make sure you're good. Same thing here, put in a 2, and down here can you input a -3. So pause the video, get your calculator out, make sure that you're doing these right, and come back and we'll check how you did. Okay, so this was the math that you should have been doing in the calculator, just to make sure we're good. And when you inputted the -2, I'm hoping that you saw 0.002. Y would have equaled -80 when you inputted the +2. And for f of -3, you should have gotten 1,600. If you're having any problems with the calculator, please let me know via email, and we can kind of check what you're doing. Final thing I want to look at is to go backwards. This is the backwards problem. What if I gave you the graph and asked you for the equation? How can we find the pieces off the graph? The first thing you're going to do is look for the y-intercept. Where does the graph hit the y-axis? And you'll notice right here, it's at 5. That y-intercept is your a. So right now, we know that the a is going to be 5. Now, the next thing we need to do is find b. And the only way we can do that is to replace the x and the y with a point on the graph. So we could use, for instance, 1 for the x, 10 for the y. So I'm going to write my equation, y, the y coordinate of this point, 10, equals, remember that the a was the y-intercept, times b, and this x was the x coordinate of this point. So the 1 took the place of the x, the 10 took the place of the y, and the 5, which is the y-intercept, took the place of the a. And now we're going to solve this for b. This is just b. And times 5, we're going to divide both sides by 5. It's a one-step equation. 10 divided by 5 is 2, and the b is 2. So now I know what my a is, and I know what my b is. So I can rewrite this. Y equals 5 times 2 to the x, and that gives me the exponential equation for the graph. I hope this gets you started on doing some graphing of exponential functions and then writing the function rules from the graph. As ever, nice to at least talk some math right now. I miss you all. Have a great day. Talk to you soon.